Hey you all, this is video 1.4.1 where I'm trying to kind of segue you from how you were finding limits analyzing graphs into how we might do the same thing if we can't look at the graph of a function, how could we still figure out what the limit is? So just kind of catch you up. You all messed around with this yesterday whenever you got to it. So you worked on finding limits. So if I wanted to find the limit as x approaches -5 of this function, I can see the left and the right side of the limit don't match. So I can say, okay, this limit doesn't exist. For this one, x is approaching 1. It's actually pretty similar to the work you're going to do today, so it looks like the limit's -6. So you all did that. You also messed around with one-sided limits. So if I wanted to find some one-sided limits, I would analyze the limit language. It's approaching 0 from the right side, so from bigger numbers. So look at the limit 7. This one, we approach 6, but from smaller values. And as I approach 6 from smaller values, it looks like it goes off to positive infinity. Khan Academy calls this unbounded. So that's the same thing, positive infinity, negative infinity, or unbounded. So you all worked with this yesterday. My prompt for you all for this is, it's not that hard to find a limit if you're given a graph, but what if we're not given a graph of function? These first three, I doubled up the assignment, so don't do this video twice, but this video, and this article are really crucial for mastering this objective. And I'm going to show off a graph that Sal Khan messed with in the very first video. And so his challenge to you in this one was find the limit. I can annotate real quick. Find the limit as x approaches 3 on this function f of x. And so if we actually analyze that, and right here is where x is 3. It looks like as I get closer and closer to that point, he makes the same conclusion in the video. The limit's probably 1.8. The y value is 1.8. But my challenge to you all in this video is, what if you don't have a graph? Can you still draw the same conclusion about what the limit is, even if you're not looking at a function? And for this, we're going to look at a function that's actually, it looks the exact same, it's slightly different. But we're going to try to find the limit of this, and we see the graph. And my suggestion to you all is, as you start to find limits using tables rather, you should always check your answer by analyzing the graph of the function. It's a really good practice to, okay, I think this is the limit, and now I'm going to graph it, and I conclude that that is the limit. But do it in that order. So if we don't have, or imagine we don't have this graph, we're going to try to figure out how could we still find this limit, and we're going to analyze it from a slightly different place. But how can we still find this limit if we don't have a graph? So I'm going to share a whiteboard screen now. So in this video, we're going to focus on this function, which I just showed you in the green. And I'm curious to know, what is the limit of this function as x approaches 5 for the function f of x. By the way, it's going to be a little annoying to write out, but I could also express that same idea, the limit as x approaches 5, and then instead of writing f of x, I can write the whole function out. That's going to be our challenge in this video, and I'm going to try to describe how we can use a table of values to draw the same conclusion we could if we had the graph of the function, which you won't always have. So the first thing when we're trying to find an exact limit using a table is I need to make sure I'm actually analyzing with the correct values. And so I want to pick values that are getting closer and closer to 5 from the left side from smaller values, and closer to 5 from the right side from bigger values. So I'm going to do a really quick just review of like what I mean by that. So let's say I made up two functions. So the limit as x approaches 4 for the function h of x. My question is like, literally what number values would I plug into the function h of x if I wanted to get an idea of what the limit was? Well, when I do this, I think about a number line. So I think about 4, and I want to think about what are values that are smaller than 4 but getting closer to it, and then what are values that are bigger than 4 but still getting closer to it. And so you'll see a lot of tables set up like this, where you have like x values and f of x values. When I think about values that are smaller than 4 but getting closer to it, I like to start with 3.5. And then I quickly progress to 3.9, which is still smaller, but it's getting a lot closer to 4. And then also 3.99. So like, as you get closer and closer to a number, if you just start adding 9s into number places, mathematically you're getting closer and as close as possible without actually being at that number. I think I'll have space at the bottom. I'm now thinking about numbers that are see if I can move you up. Oh, that didn't work at all. Think about numbers that are bigger than 4, but getting closer to it. I like to start with 4.5. Now, in most tables you'll see drawn out, they would have like the next smallest number right next to, I'll show that too at the end, but I could also pick 4.1. So I'm getting a lot closer to 4. And then as I want to get really close but not get to 4, I start adding zeros in those place values. So 4.01, and then I'm going to have space at the bottom, so I'll put 4.001. So I just reorganized that table. So if you saw a table, it would be organized from, like, it wouldn't just jump to 4.5 here. It would have like that next closest value, but not exactly at 4 in the table setup. But what we do is we take all these values and we plug it into, and I mislabeled that. That should be h of x. That's the function we're analyzing here. And we would just plug these x values, just regular substitution. We plug it in, we see what the y value is, and then we see, are the y values approaching the same value? If they are, we conclude that that would be whatever the limit would be, the value that they seem to be approaching. And I can also do a table sort of like horizontally, but the setup starts the exact same. So if I want to figure out, okay, what is the limit as x approaches -7 of this function m of x, I want to figure out what are values that are smaller than -7, but getting closer. So I like to start with, I'll do x values and I'll do m of x values, and I will almost certainly run out of space, but it's fine, I'll try my best. So I like to start with -7.5, reminder that is smaller than -7, and then quickly go to -7.1. And then if I want to get closer to a number, but not get all the way there, I can add a 0 into like the place value just to the right of the decimal. And then I would do -7.001 and so on and so forth. And then if I want it to be just bigger than -7, do that. Again, just barely bigger would be -6.99. So it's not at -7. But again, if I'm closer to 0, I am a bigger number than whatever the negative number is. And then -6.9. And then -6.5. And so same thing, I would just plug those values in for m of x. I would just plug those in and figure out the y values. And if they seem to be approaching the same y value as we get closer and closer to the limit, we'd say whatever that number is, well, that's the limit for this function. I wonder if I can. All right, so I set up the table I'm going to use to analyze this function. I changed it to g of x because it was g of x on Desmos. Now you can imagine if I plug in 4.5 to this, 4.5 to the third minus 5, quantity 4.5 squared, and then divided by 5 times 4.5 minus 25, it's going to be a pain. I would never do it by hand. It's even going to be a pain to plug into your calculator. So I want to show you a quick trick that I hope will help you out if you're using a graphing calculator. You can also use Desmos, and it works out really well too. I'm going to stop sharing and show just a graphing calculator. One trick you can do, the first number I wanted to analyze was 4.5. So what you can do is type in the number, and then right down here in your calculator, this STO button with a little arrow, it allows you to store values and save them for later. And then I want to put this button right here next to alpha, has an X in front. So it's like it can be used as your variable button. So now what's cool is every time I type in X, 4.5 comes up. And so what I'm going to do is type the function. I'm going to make it into, my face is in the way. Please go over there, bud. So I'm going to do the numerator and denominator setup, and I want to type in the function x to the third, and I believe it was minus 5x squared. I hope that's right. Then on the bottom, I believe it was 5x, and then minus 25. I'm going to pause real quick. It should be 5x squared. Yep, I got it, cool. So now, going back to my calculator, so now what's really cool is if I just hit enter, because I already saved that x value. I don't want this to be full screen, come on though. If I just hit enter, then I get the actual y value, and I can go math. I actually want to know it as a decimal, it's a little easier to evaluate that way, and I get 4.05. So I'm going to do this for a few more examples and just write my numbers up. But I can now, I still have it stored, I want to try out 4.9, so I'll do 4.9 and I'll store that value in X. And then instead of retyping this each time, you can go second enter on your calculator and just keep pressing second enter, and it'll pull up previous entries. And now I can get here and just hit enter. And I'm going to change that value into a decimal. So I have 4.05 for 4.5. When X was 4.9, I have 4.802. I can do one more that'll show you 4.99. I'll store that in X. Then I'll go second enter until I get back to the function I want. And then when we plug in 4.99, it's 4.98. So you can see it's getting closer and closer to a certain number. All right, so I finished this analysis. What I would do is try that calculator trick or try in Desmos to make sure you're getting the exact same values. When I plug in all of these X values, here are the Y values I got. So what's really cool is we can see that as we get closer and closer to when X is 5 on both sides, we seem to be getting, just in this case, not in all cases, we just seem to be approaching the same Y value, which is 5. So we could conclude that the limit as X approaches 5 of the function g of X is equal to 5. And so last point I want to make for this video is that if we just look at the graph, sweet. It looks like that's, if I get closer and closer to where X is 5, it looks like it's approaching 5. What's interesting is if I actually get to that point, it's undefined. And so one point you're going to learn in these following videos is that the limit, as I approach a certain value, does not have to be the same as the output value. The limit might be different from the actual defined value at that point. So maybe this function has the point 5, 7. So I'll label that point. So maybe this function, as we get closer to 5, the actual, if I plugged in g of 5, I would get out 7. It's not true in this case. But just because the limit is approaching a certain value does not always mean the output value is the same for that function. And that's when you'll learn in these following videos. I hope that was helpful. As always, let me know if you have questions.